Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is secondary resistor reduced voltage starters. Our objective is to examine both hardwire relay-based ladder logic and programmable logic controller or PLC-based implementations of secondary resistor reduced voltage starters used to reduce inrush current demand for wound rotor induction motors. This lecture operates under the presumption the viewer has watched the wound rotor induction motor lecture, and those lectures comprising the reduced voltage starters and timers playlists available at the Big Bad Tech channel. If you haven't watched these lectures yet or only dimly recall their contents, please bring yourself up to speed and return when you're so qualified. As you are no doubt aware, the direct and instantaneous application of full voltage to a motor at standstill produces a tremendous surge of current known as inrush. You should be as tired of hearing this as I am of saying it. Although brief, inrush can place unnecessarily high demand on the electrical distribution network, and industries often pay a financial penalty for such events. It is for this reason various types of reduced voltage starting methods are employed, all of which serve to limit both inrush current and modify the starting torque of a motor under the direction. In the aforementioned motor control playlist, we examined several types of reduced voltage starting methods, including but not limited to primary resistor reduced voltage starters, part winding reduced voltage starters, Y start delta run reduced voltage starters, soft starters, and motor drives. In these applications, we limited our discussion to squirrel cage induction motors, a common type of three-phase AC induction motor. While these same methods are applicable to other types of motors also offer alternate reduced voltage starting methods based upon their construction and theory of operation. Case in point, consider wound rotor induction motors. Wound rotor induction motors, since they offer accessibility to the rotor via a set of slip rings, allow a degree of rotor customization not possible with a fixed resistance rotor squirrel cage induction motor. As we learned in the aforementioned wound rotor induction motor lecture available at the Big Bad Tech channel, wound rotor induction motors with low resistance rotors behave like Design B squirrel cage induction motors and operate relatively efficiently at high speeds. This being said, they don't exert terribly high starting torque and are known to experience a large surge of inrush upon start. Conversely, wound rotor induction motors with high resistance rotors behave like Design D squirrel cage induction motors and exert high torque at low speeds with less inrush at the start. This being said, they're not known for outstanding efficiency. Consider these plots of inrush current upon closure of a full voltage starter for two different rotor configurations experiencing 1 Nm of counter torque. A low resistance Design B style rotor at the top and a high resistance Design D style rotor at the bottom. In the slightly loaded condition, it looks like the low resistance rotor experienced an inrush current peaking out at maybe 8 amps? That seems a little over the top for something that might be drawing 1 amp RMS in the steady state condition. In contrast, the high resistance rotor experiences only a peak at most of maybe 6 amps, a far more reasonable and achievable demand. This being said, if we kept it in this high resistance condition for long, we wouldn't expect it to operate that efficiently. Wouldn't it be great if you had the high torque starting ability and low inrush current demand of a high resistance Design D rotor, and when the load is actually moving, switch over to a low resistance Design B rotor such that it operates more efficiently at high rotational speed? We'll check it out. Wound rotor induction motors employing secondary resistor reduced voltage starters allow this stage transition from high resistance start to a low resistance run mode. Or allow me to demonstrate. One way of toggling between high and no resistance operation is with a shunt contactor in parallel to an external bank of resistors. When the shunt contactor is open, the external resistor bank is placed in series with the rotor, and the motor operates like a high resistance Design D squirrel cage induction motor. In contrast, when the shunt contactor closes, the resistor bank is shorted out or bypassed, excluding them from the rotor circuit, and the motor operates like a low resistance Design B squirrel cage induction motor. As you may have guessed, a secondary resistor reduced voltage starter starts the motor with the shunt contactor open, such that the motor exerts high starting torque with lower inrush, then after a predetermined period of time, closes the shunt contactor such that the motor operates more efficiently at higher speeds. Consider a hardwired, relay-based ladder logic implementation of a secondary resistor reduced voltage starter employing a timer executing the on delay function. Viewers will recall an on delay, sometimes called a delay on energize or DOE, or slow operating or SO timer, exhibit a customizable delay time between when the timer coil is energized and when the associated contacts change states. When the timer coil is energized, the associated normally closed contact remains closed and the normally open contact remains open. Only after a predetermined time delay, TD, is elapsed, do the normally closed contacts open and the normally open contacts close. When the timer coil is de-energized, the associated contacts return to their deactivated states, i.e. the normally closed contact recloses and the normally open contact reopens. You'll sometimes see the contacts executing the on-delay, delay on energize, or slow operating function using an arrow to signify which operation is being delayed. Here's a symbol for a normally closed, time-open contact, often abbreviated NCTO. The contact is drawn normally closed, however the arrow indicates the opening of the contact is delayed after the coil has been energized for a predetermined time. Similarly, here's a symbol for a normally open time-closed contact, often abbreviated as NOTC. The contact is drawn normally open, however the arrow indicates the closing of the contact is delayed after the coil has been energized for a predetermined time. As helpful and informative as these schematic symbols are, for some reason they've fallen out of favor, and you may just see a contact associated with a timer illustrated as a regular normally closed or normally open contact, as in this implementation. The primary circuit consists of the M contactor in series with an overload on the stator windings, and a shunt contactor S and an external resistor bank on the slip rings on the rotor. Key to this particular application is the controlled closure of the S shunt contactor. We first want the M contactor to close and energize the wound rotor induction motor stator with the shunt contactor open such that the secondary resistors are included in the rotor circuit. Then after a predetermined period of time, let's say 3 seconds has elapsed, close the shunt contactor such that the secondary resistors are shorted out and excluded from the rotor circuit. The top 3 rungs of the pilot circuit largely concern the M contactor, whereas rungs 4 and 5 concern themselves with the timer and the shunt contactor. Rung 1 consists of the series combination of a normally closed E-stop, a normally closed stop, a normally open start, a coil of control relay CR1, and a normally closed thermal overload. All the normally closed devices serve to de-energize CR1 in the event of an operator-initiated stop, an emergency, or a sustained overload. An operator can start the system by closing the start button, which energizes the coil of CR1. When CR1 energizes, its associated contacts in rung 2, 3, and 4 simultaneously change states. The CR1 contact in rung 2 closes and establishes a holding circuit, allowing an operator to release start. The CR1 contact in rung 3 closes and energizes the M primary contactor coil. The M contactor closes and the motor starts. Importantly, the motor starts in the high resistance configuration since the shunt contactor is open. In high resistance mode, the motor exerts high starting torque and experiences notably less inrush. The motor accelerates. Lastly, the CR1 contact in rung 4 closes and energizes the coil of timer 1, executing the on-delay, DOE, or SO function. Given the timer is executing a delay on energize function, its associated contacts, notably TR1 in rung 5, remains open until the delay is elapsed. This being said, the clock is running. 3 seconds later, the timer completes the on-delay function, and the TR1 contact in rung 5 closes, energizing the shunt contactor coil. Shunt contactor closes, shorts out the resistor bank, and the motor transitions to low resistance mode, suitable for high-speed, efficient operation. An operator wishing to stop the system and reset the starting state would press and release stop. Here's a real-time simulation of this circuit using Automation Studio. As we illustrated in the walkthrough, an operator presses and releases start to close the M contactor, establish a holding circuit, and start the timer. 3 seconds later, the timer reaches its count and closes the shunt contactor, shorting out the resistor bank. As we anticipated, the motor starts in high resistance mode with high starting torque and less inrush. After a predetermined delay, allowing a degree of time to accelerate, the shunt contactor shorts out the resistor bank, and the motor switches to low resistance mode, suitable for high-speed, efficient operation. Here's the system in operation once again. Secondary resistor reduced voltage starters can also be implemented using a programmable logic controller, or PLC. One of the major advantages of PLC is that they are reprogrammable devices and do not need to be rewired to change functionality. Consider the selection of hardware connected to a PLC input and output card in the following fashion. On the input side, normally closed stop is wired to digital input 0, normally open start is wired to digital input 1, and finally auxiliary contact M1 associated with the M primary contactor is wired to digital input 2. On the output side, the coil of the M primary contactor is wired to digital output 0, and the coil of the shunt contactor S is wired to digital output 1. Viewers will note the normally closed e-stop is hardwired to break the connection of pilot level voltage to all input and all output elements without the involvement of the programmed instructions. Viewers will additionally note the M1 auxiliary contact on digital input 2 serves to convey real-world feedback to the PLC about the status of the M contactor. Finally, viewers will note the normally closed overload is hardwired in series with a parallel connection to the M and S coils, thus serving to de-energize both these output elements without involvement of the programmed instructions. Long story short, never trust a computer. Anytime the e-stop or overload opens, regardless of what the PLC program is telling it to do, the system will not energize the M or S contactor coils. It is my sincere recommendation to have this level of safety redundancy in any system you work on. Let's take a look at the program. It's very similar to the hardwire relay-based ladder logic implementation. Rung 1 consists of the series connection of two make instructions scanning digital inputs 0 and 1, the stop and start push buttons. For digital output 0, the M contactor to energize, both the stop and the start button must be closed. Rung 2 is a holding circuit based on the real-world status of the M contactor rather than some programmed instruction. If the M contactor truly closes, the M1 auxiliary contact closes, and digital input 2 establishes a holding circuit. Digital input 2 in rung 3 also starts a timer with a 3-second preset executing the DOE function. When the timer is complete, the timer done instruction in rung 4 energizes digital output 1, the shunt contactor. An operator can press and release stop to stop the motor and reset the system. Here's a real-time simulation of this circuit using Automation Studio. As we illustrated in the walkthrough, an operator presses and releases start to close the M contactor, which establishes a holding circuit and starts the timer. 3 seconds later, the timer reaches its count and closes the shunt contactor, shorting out the resistor bank. As we anticipated, the motor starts in high resistance mode with high starting torque and less inrush. After a predetermined delay allowing for a degree of acceleration, the shunt contactor shorts out the rotor resistance bank and the motor switches to low resistance mode, suitable for high-speed, efficient operation. Here's the system in operation once again. In summary, the PLC implementation behaves exactly like the hardwire relay-based ladder logic implementation, only the PLC version is reprogrammable. Case in point, consider the heartbreaking labor involved in modifying the previous secondary resistor reduced voltage starter to include not one, but rather 4 banks of starting resistors and shunt contactors. When all shunt contactors are open, resistors A, B, C, and D are placed in series with the rotor, thus the rotor experiences maximum resistance. When shunt contactor 1 closes, only resistors B, C, and D are placed in series with the rotor, thus the rotor experiences less resistance. Similarly, when shunt contactor 2 closes, only resistors C and D are placed in series with the rotor, thus the rotor experiences less and less resistance, and so on. Stage closures of shunt contactors 1, 2, 3, and then 4 allow a more gradual transition from high to medium to low to no resistance in the rotor circuit. The staged secondary resistor reduced voltage starter might be suitable for a larger load that takes some time to bring up to speed. The first 5 rungs are essentially repeats of our original single-stage hardwire relay-based ladder logic implementation, which closes the M contactor on the stator, establishes a holding circuit, and starts timer 1. 3 seconds later, timer 1 energizes the S1 shunt contactor coil. The S1 shunt contactor closes and shorts out resistors bank A. The additional rungs control the remaining shunt contactors and their associated timers. When shunt contactor S1 closes, the auxiliary S1 contact closes in rung 6 also and energizes timer 2. 3 seconds later, when timer 2 completes the on-delay function, it closes the timer 2 contact in rung 7 and energizes the S2 shunt contactor coil. The S2 shunt contactor closes and shorts out resistor banks A and B. Simultaneously, auxiliary S2 contact closes in rung 8 and energizes timer 3. 3 seconds later, when timer 3 completes the on-delay function, it closes the timer 3 contact in rung 9 and energizes the S3 shunt contactor coil. The S3 shunt contactor closes and shorts out resistor banks C, B, and A. Finally, when auxiliary S3 contact closes in rung 10, it energizes timer 4. 3 seconds later, when timer 4 completes the on-delay function, It closes the timer 4 contact in rung 11 and energizes the S4 shunt contactor coil. The S4 shunt contactor closes and shorts out resistor bank D, C, B, and A. An operator can press and release stop to stop the motor and reset the system. What you get is this staged transition from high to medium to low to no rotor resistance, suitable for a heavy load that takes some time to bring up to speed. Here's a real-time simulation of this circuit using Automation Studio. As we illustrated in the walkthrough, an operator presses and releases start to close the M contactor, establish a holding circuit, and start timer 1. 3 seconds later, timer 1 reaches its count and closes shunt contactor S1, shorting out resistor bank A. 3 seconds later, timer 2 reaches its count, closes shunt contactor 2, shorting out resistor bank B and A. 3 seconds later, timer 3 reaches its count, closes shunt contactor S3, shorting out resistor bank C, B, and A. And finally, 3 seconds later, timer 4 reaches its count and closes shunt contactor S4, shorting out the resistor bank D, C, B, and A. As we anticipated, the motor starts in high, transitions to medium, then to low, and then to no resistance mode. Here's the system in operation once again. In summary, by rewiring the hardwire relay-based ladder logic implementation, it gained new functionality. This being said, imagine all the heartbreaking work that went into this. Look at this. You're adding like 3 extra coils, 3 extra auxiliary contacts, 3 extra timers, 3 extra timer contacts, and what, like a minimum of 18 extra wires? Someone is bound to screw this up, and even if they don't screw up, it'll take all day to get it done. Think of this as just one of hundreds of systems that needed this modification. There has got to be a better way. One easier method might be to make use of a reprogrammable PLC. The PLC implementation necessitates only 3 additional shunt contactors, S2, S3, and S4. Absolutely no additional hardware is necessary. New functionality can be gained simply by reprogramming it. Let's take a look at the program. The first 4 rungs are repeats of our previous PLC implementation, where if an operator presses and releases the start push button on digital input 1, it energizes the M contactor coil on digital output 0, establishes a holding circuit with the M auxiliary contact on digital input 2, and starts timer 1 in rung 3. 3 seconds later, timer 1 energizes the S1 shunt contactor coil on digital output 1. The S1 shunt contactor closes and shorts out resistor bank A. The additional rungs control the remaining shunt contactors and their associated timers. When digital output 1 is energized, it also starts timer 2 in rung 5. 3 seconds later, when timer 2 completes the on-delay function, it energizes digital output 2 in rung 6. The S2 shunt contactor closes and shorts out resistor banks B and A. When digital output 2 is energized, it also starts timer 3 in rung 7. 3 seconds later, when timer 3 completes the on-delay function, it energizes digital output 3 in rung 8. The S3 shunt contactor closes and shorts out resistor banks C, B, and A. Finally, when digital output 3 is energized, it also starts timer 4 in rung 9. 3 seconds later, when timer 4 completes the on-delay function, it energizes digital output 4 in rung 10. The S4 shunt contactor closes and shorts out resistor bank D, C, B, and A. As with a hardwire relay-based ladder logic implementation, what you get is this staged transition from high to medium to low to no rotor resistance, suitable for a heavy load that takes some time to bring up to speed. An operator can press and release stop to stop the motor and reset the system. Here's a real-time simulation of this circuit using Automation Studio. As we illustrated in the walkthrough, an operator presses and releases start to close the M contactor, establish a holding circuit, and start timer 1. 3 seconds later, timer 1 reaches its count and closes shunt contactor S1, shorting out resistor bank A. 3 seconds later, timer 2 reaches its count, closes shunt contactor 2, shorting out resistor bank B and A. 3 seconds later, timer 3 reaches its count, closes shunt contactor S3, shorting out resistor bank C, B, and A. And finally, 3 seconds later, timer 4 reaches its count and closes shunt contactor S4, shorting out the resistor bank D, C, B, and A. As we anticipated, the motor starts in high, transitions to medium, then to low, and then to no resistance mode. In summary, by reprogramming rather than rewiring the PLC, it gained new functionality. Trust me, reprogramming sure beats rewiring, especially if this is just one of many systems necessitating this modification. All right, that's all I've got for you today. In conclusion, this lecture examined hardwire relay-based ladder logic and programmable logic controller, or PLC-based implementations of single-step and stage secondary resistor reduced voltage starters used to reduce inrush current demand for wound rotor induction motors. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.